So again, welcome everybody. We are covering data review today. So big picture, we've done a couple of webinars in this series. First on putting data into ARM and kind of confirming that that data typed in is correct. Then we took a look at the data collection options for getting the numbers and the values into the software. And then today we're kind of taking that information now that the data is in there and preparing it for the analysis. So there's kind of a step in between just wanting to run it through and look at their numbers and find our letters and what separations and things like that. But we want to kind of talk through the process of actually preparing the data for that. So before I dive into the software, I want to cover just kind of an overview, kind of quick, on the just the statistics in general that we have in ARM. Kind of sets the stage, I think, for us in understanding the tools that we will be showing then in ARM. So I'll kind of go quickly through this so we don't have to burn our whole time on it. But in general, the goal of research is, determining whether treatments of interest perform differently or the same. And your choice of treatments, depends on your research. Could be different products, different formulations, different rates. But the big thing is to, know if those treatments can be distinguished from another. If it's effectiveness, safety or cost, or sometimes maybe if your product is cheaper, you hope the performance isn't, distinguishable and it's all the same. So of course, your running research trials are performed. That way we can obtain observations of that performance. In ARM, we call them either assessments or ratings, is what I'll refer to them as. But then the big question is, are those differences that we saw due to the treatments themselves or by random chance? And so that's really where the statistics come in our case, specifically the analysis of variance. We kind of touched on this in the previous session about the data confirmation. So you don't want to just immediately jump into number crunching as soon as the data is there. So you want to make sure that putting the values in your assessments in, that you catch any outliers and issues with the assessment before going ahead and analyzing it. So, an outlier is going to really cause problems in the assumptions of AOV that we'll kind of talk about here soon. And so, that's really why we had that separate session to talk about kind of trying to catch those problems. And so, keeping a lot of detailed records and using some of those data collection tools to help you take a glance at that data as you're putting it in is important for that. So looking kind of then at the analysis, agriculture research is always going to be subject to variation. And it's from a variety of sources. So we're performing an analysis of variance on the data. And so, really the statistical variance is a measure of how spread out the data is, up from its mean. Sometimes called ANOVA or AOV, we're really dissecting the variability in your recorded assessments. So there's controlled variability that's from your treatments and the blocking structure that was used. And the experimental error is the uncontrolled. And so we're really looking at if the observed differences are just due to chance, then the variance between the treatments would agree with the variance within the treatments. It's really roughly kind of what we're setting out to answer. Just real quick example of the analysis with the AOV, just to define the components, and I'll just go real quick because it's not terribly specific to the data review, but the degrees of freedom is the number of values in a final calculation that are free to vary. kind of hard to define, but with variance, the degrees of freedom is n-1. So in this case, we'd have 4 degrees of freedom, and then you get the sum of squares. That is really the total amount of variation in the data, which we split up by each source. Then the mean square is the sum of squares divided by the degrees of freedom, really thinking of the amount of variation divided by the degree to which it can occur. Then we do an F ratio. That really indicates the level of variation from that source compared to the random variation. So of course, the larger that value is, the more likely that the variance from that particular source is not due to just random chance. So to kind of try to nail that down into a number, we calculate a p-value, which is the probability that observed differences in the treatment or the block means could have arisen by chance. So if you have a low p-value, typically we say less than 5%, would indicate that we can be confident that real differences exist. Whereas if you have a high p-value, like we have here between the blocks, really tells us that there's no evidence of a real difference. It could be because there is no real difference, or the differences are just too small for us to detect. And so, again, overall, we're really breaking apart the variance of our observations into different sources. And then the end result is a nice simple p-value that we can look at. And that really is a probability. And specifically for our case with the AOV, it's the probability that no differences in treatments exist. So if our p-value is 0.04, then we're 96% confident that there are significant differences. We're not done yet, though. We want to know which observed differences between the treatments are significant and which are not. So we do mean comparison tests. And so, we're really just comparing the specific treatment means to determine what differences are significant. And we've got quite a few options in ARM. The most common ones here are listed, but there's, I think, a few other ones as well available. And you can kind of talk through the rationale of which ones to choose. Won't really get too deep into that, but really it's a matter of managing your type 1 or type 2 error, whether you're more worried about a false positive or a false negative. And a good way to think of that is your penalty of failure for the study. If your trial, if you're going to register a trial, then being more conservative makes a lot more sense. But if it's just screening, it's all about potential. So you would want to kind of decide which route to go based on that. We've got a handout if you're interested there on that link that dives into each one of those tests on the previous screen a little more in depth. And of course, the big finale that people want is the letters, the way to kind of describe the differences. We won't really go through the steps here, I think, but really we're calculating a test statistic and then comparing the means with them and give them letters. So that's the analysis. That's our target where we want to land for really looking at the data that we have in. Really, the big focus today is the fact that all of that analysis we did there has some requirements. We're assuming certain things about the data in order to do that whole process we just described. And so if the data that we are using doesn't match up with those assumptions, we really can't trust any of the things we just got done doing or talking about in the analysis. So that's really the purpose of the tools that to discuss today with the data review is to zero in on these assumptions of ANOVA. So the first one is homogeneity of variance, and that it means that the variances within the treatments are approximately equal. Another way to say it, if a treatment is much more variable, or maybe much less variable than the others, then ANOVA isn't going to work. So, to determine, whether this is the case, we could use a box whisker graph or run a specific statistical test for homogeneity of variance. Levine's is generally chosen, but we also have Bartlett's in ARM as well, depending on what you're used to. The next requirement is that the data is normally distributed. So if your data isn't, approximately bell-shaped, then you can't use the same p-values in the analysis. As Peter, our statistician, would say, it's just math. So a few tests for this include the skewness, kurtosis, and also Shapiro-Wilks to tell us whether we can assume our data is at least, generally follows a bell-shaped curve. Then finally, the last two assumptions, independence of errors and additivity of treatment and block effects. These are harder to test, usually are not a big issue in the agriculture research. The biggest thing really is to not introduce bias in the assessment. So things like edge effects or subjective ratings that that are influenced when you're taking the notes, things like that. So just tool-wise within ARM, I think the assessment map would be maybe the best one to be able to detect some of those things if there was a concern to look at them. And that, like we kind of saw that tool last time in the data confirmation steps, and also in some of our data collection tools as well. So what happens if those assumptions are not met? Well, we have data correction transformations, which are designed to really correct the underlying distribution of the data without affecting the results. So there's three main ones here that can be used. The logarithm, that's good for counts of things that occur in clusters. So, assuming a log normal distribution, I think is the name for that one. Then there's a square root transformation. That's typically for counts of things that occur at random or occur real rarely. So you'd have typically a lot of zeros and then a 1 or a 2 here or there, but most often the assessment value itself is just a 0. And that would be a Poisson distribution that follows. So, never going to be bell-shaped, but follows that particular pattern. And then the last one is the arcsine square root percent. And that really is great for percentage data that follows a binomial distribution. We also have spatial models. Those try to recover information about hidden variables across the field. Within ARM, we have 3 trend and 4 nearest neighbor models that can be used. Typically, that's kind of a last ditch effort. You wouldn't immediately jump to that tool, but it would be used when your blocking design fails, is when that's most useful. We won't spend a ton of time on that today. And then the last option, and we'll cover that in ARM as well, non-parametric statistics. So that actually just totally throws out AOV, that whole process and its assumptions. Really we are analyzing the data by ranking the individual assessment values. Then a mean comparison test can be run on the mean of those ranks instead of the values themselves. So we're kind of sidestepping, if we can't do anything else, kind of sidestep the whole issue with the assumptions of AOV and do this different type of statistics and non-parametric. So that's really what we're focusing here in ARM then, is the tools to check for these assumptions and then implement some of these items here if we need to. let me close out of that and we can get into ARM. So here I've got a trial open, kind of rigged up a little bit to give us a few examples of different assessments that are available to us to review. And so the primary tool that we'll want to use today is the column Diagnostics. So that is over on the far right side. We have a properties panel here. And then a little more to the right there, all the way on the side, there's a couple of hidden panels that we can expand. And the first one here for me is column Diagnostics. So if I click on that name, I can see the panel. I'm going to pin that panel down so it stays open for me. And actually, I'm going to unpin this properties panel. So that way I have more space just for this one. And let me adjust this out a little way so we have some more horizontal space. And we'll try to share the screen a little bit. All right, so this column Diagnostics is kind of split up into a couple of sections. We'll just take them one by one. And this top half is the Diagnostics table. First off here, kind of just gives us some stats, if you will, almost like a the stat sheet from a sports game or something, of just giving us a rundown of whichever assessment column we are clicked in. So if I click over to number 2, you're going to see everything recalculate on the panel, and then going back to 1, it'll switch over. So whichever column that you're clicked into on the left, this panel on the right now will refresh and show us information about that assessment. So we've got 24 values in this trial, so 24 different plots. And we can see that just in this assessment, there's only 11 unique values. It'll give us an indication of how many values are missing, empty, or marked as damaged. So this is kind of a nice potential tool, kind of in that data confirmation step to see if we were expecting missing values or not. It'd be an easy way to catch something if we missed putting in a value. And if we were missing an entire replicate or something like that, those values are all kind of helpful for that. The next section here, starting with Levine's, I'll scroll down just a little bit more, are really the big thing we came here for, I guess we could say. These are really those tests for the assumptions of AOV that we alluded to earlier. So these, we are running those tests to determine if we have any concerns about the assumptions of AOV. And here in this first column, we have the values related to the raw data, and these are p-values. So really looking at the value, if the number here is significant, and therefore low, or if it's at 5% alpha level, we'll say in our case, if it's below that 5% threshold, then we have a problem. Then we're concerned because our test is failing, and we would need to look further. So this is run on the raw data here in this first column. And then the second column labeled IID is actually looking at the residuals of the data. So that's one key difference here in this slightly newer tool than some of the other data review tools in ARM, is a little more modern approach. So statistically, this is a little more modern way to look at the tests based on the residuals of the data instead. So that's really where we want to go first, to kind of look to see, do we think we have any issues? And in this first trial, or this first assessment, nothing really pops up for us that I can tell. They're all not significant. So If you don't want to look directly at the values, or you want kind of a nice summary of what we're expecting in case you don't remember how to interpret those numbers, we can move down to the second section here of the table, which is the recommendations. So not only will we just kind of run the numbers and give you the numbers for you, ARM kind of has an engine here to assist with making some decisions based on that information. So we'll see in this table that for each of those 4 test statistics, the Levine's was for the homogeneity of variance, and then Shapiro-Wilks, skewness, and kurtosis were all kind of related to the normality. Each one of those tests, we have the value of the test statistic. ARM looks to see what actions should we take, if any. And in this case, like we had noted above, none of the values were significant, so there really is no action that we would need to take. There's no data correction or anything that we would need to do. We have a green light to proceed to the AOV analysis. Everything looks great. So we kind of see this IID again. This is kind of an action code that we have to kind of pretty much be a little check mark to say, I've reviewed this column and there was no correction, there was no action needed. So what I can do is just double click on this first row here, the IID, and that will put in that action code here in this column. And in this case, it's not much of an action code because it's really just an inaction telling us we don't need to do anything. But it's a nice way to kind of mark that this has been reviewed. If you just left the action code blank and someone returned, did somebody look at this column or did they not? IID is a nice way to say, yep, I looked at it and there is no action necessary. So we can move to the next column. There's a button down here on the properties panel, or we could have just clicked into the second column. And we can really do this all again. If we wanted to, we can come up here and look at the diagnostics panel and look at the numbers. We see right away 0.02 is a lot smaller than we were seeing before. That is significant. So we have an issue. And so typically for me, my eyes kind of go right down to the recommendations. This is kind of the moral of the story, if you will, to look at real quick. If all of them are IID, we know we're good and we can move on. But the fact that we have something else here tells us we should slow down and take a closer look. So this is telling us that the Levine's test is failing. And if we add the AL, the log transformation, that would stabilize the variance. We can actually kind of customize this recommendation engine by looking at this basis option. So right now we have it set to assessment values. So ARM is just looking at the individual values themselves and figuring out what would work. In this case, the first one it checked was AL, and lo and behold, that the Levine's test, if we perform the log transformation on the data, the Levine's test passes. So that would be a suitable action for us. But we can kind of sharpen ARM's recommendations by giving it a little more information. Instead of just looking at the numbers, we can tell ARM to consider the rating type, which in our case is a count. And if I choose that, you'll see actually our recommendation changes. So now that ARM knows that this is count data, it knows that actually, typically the square root transformation is preferred for count data. And so the AS is recommended because number one, we have count data, and number two, performing the AS transformation, then the Levine's test will pass. So we can do the same thing whether it's the rating type or the rating unit. to give ARM an idea of what it is that we're dealing with. So just looking at that rating type, just to draw a connection here, this family column that's been added somewhat recently relative to the rest of this list is really kind of where the brains of that decision making comes into the fold. So it knows that this is count data, whereas there's a proportion or percent is a totally different type of assessment. So that's kind of what ARM is keying off of to understand what we're looking at, really. So in our case, we said the basis was count data. ARM said, great, then square root would be your best choice. So I'm simply going to, I could either double click again on this row, or if I was looking at this table here, I can click the checkbox next to AS. Either one of them will put in that action code into this column. And again, what this will do is when we go to analyze the data, ARM will perform the square root transformation on the data, perform the AOV analysis, and then present the results. So the original data is not being touched. We haven't changed anything here on the screen. It's simply instructions for when we go and run the statistics in the report. Then we can do what we need to do to get our results, essentially. All right, one more tool here while we're looking at this column and trying to make a decision. I guess we kind of made that decision anyway, but we have one other functionality here. There are diagnostic graphs. So if we really want to dive in to kind of get a closer look at the data, let me actually backtrack to column 1 first. And so you'll notice that the text of this graph changes just depending on which code I have selected. In this case, all of them are IID, so it's going to give me the IID graphs. And I'm just going to press, give me the 2x2. This just controls how many graphs print on a page, because you'll see it's going to give us a PDF document with these diagnostic graphs. And so if we had the IID selected, so there isn't a transformation necessarily to look at right now, then what we have on the left is the raw assessment numbers, and we have a box whisker graph. We have a normal QQ plot to look at kind of the normality. If I go to page 2, on the left, there's a spread location to give us a sense of any skewness. And then finally, there's a histogram of the values as well. Going back to page 1, we have the very same type of graph on the right, but the difference is this is the residuals. So this is where we really want to be making our decision for whether we should be applying a data correction or not. I'll admit I'm not a master in all of these graphs, but they are nice visualizations. In this case, the box whisker we touched on a couple of weeks ago, giving you a sense of the variability in each treatment. So just the height of the box for each of the treatments here gives you a rough idea of the variance. And so we, of course, would want these box heights to be pretty close to each other. We don't really care if they were all tall or all small, just that they all were about the same is what we're looking at for that homogeneity of variance. We see the p-value is very strong, so we have no doubt that those variances are similar enough for us. The normal QQ is giving us the sense of normality, and we have the lines of 2 and 3 standard deviations, getting a sense of how many individual plot values are outside of those bounds. this isn't bad. 0.524, again, we're really not concerned of using that. The next graph here, I think you're hoping for nothing too much of a pattern. So this one is a little shaky, but here on the residuals graph, much more random. So we're happy with that, and that p-value kind of confirms it. And then the histogram, again, you're looking for a bell shape. And really the kurtosis is how peaked that bell is. So here we have maybe a little bit of a concern because this one's a little high, but not a big enough one. So that's a good tool here just to see and really dive into some of the statistics and the numbers that we have if needed. If I move to the next column, just to show the graph one more time, but if you have a data transformation selected when you generate the graph, we have the AOV residuals, so just the same graphs that we saw last time on the right, they're over here on the left. So this is the data without any transformation applied. And you'll be able to then see the problem. In this case, we have treatment number 1 has a lot of variability, whereas the rest of these are smaller variability, and that's kind of where we got tripped up in our analysis. Then on the right is the proposed action code, kind of the results, if you will, of those tests if we were to perform that action. So now we can see that the variability is better. Maybe not perfect quite yet, but definitely better. We can feel good about sending those into the AOV analysis. And we could, of course, scroll through the rest of the graphs to make sure we weren't breaking anything else in the process. So that's the graphs, the exact same thing up here. So just depending on whether you're clicked into one of these columns, which are the different possible actions, or the recommendations here, which are also actions, what diagnostic graph you might want to look at. And just to mention, those are PDF documents. So if you needed to utilize those in anything else, it's real nice to have that file and pull it somewhere else. Or utilize it in something else. All right, so that took kind of a while to explain the process, and I fear that sometimes that makes it seem like this is kind of a hard process to do. But really, it's pretty quick to review the data. You can just press next and go to the next column. And as I said, personally, for me, my eyes jump immediately to this list. And I see all 4 IIDs. I know everything is great. I'm pretty happy with that. I'm not even going to bother looking at all these other numbers or the graphs. I'm just going to press next. Okay, then I need to slow down here. My eyes looked right at this list and I saw something other than IID. And so now I'd want to slow down a little bit. And if it's stats junky, we could look up here or print those graphs. For me, if I want to be real simple, I'm just going to take a look and say, all right, my rating type is the helpful thing. I can tell ARM this is count. And so I trust that AS is a good choice. So I'll just double click and continue on. Oh, great, all IID. Just double click and keep moving. Same thing here, nice and simple. Same thing here. So we can really kind of cruise through these columns because they're all just, quite a few of them at least, all have no concerns for us, which is great. And so hopefully it doesn't seem quite as intimidating here, just running through these. I think we're getting pretty close to the And you'll notice here, I did have an action code already. We had calculated, this is a calculated column, specifically in AUDPC, that IID just gets added. There's just a space and it just gets added. So there's just more information, individual codes that show up, not a problem for ARM. All right, so this one here, now we need to stop because we've got a few, actually a couple of things wrong here. Number one, I noticed that my basis, it says there's no rating type family. So basically ARM says, I don't know what this lodging is from a mathematical standpoint. I don't have any pattern I can apply. So that would be one cue that this choice isn't going to help me much. Maybe if I change my rating unit, ARM will be a little smarter for me then as to what action codes it might recommend. Now the second issue here, I guess different than what we've seen previously, is before it was always Levine's that was failing. Now we have a couple of, the Levine's is not, so we have a recommendation for IID, but the Shapiro-Wilks has a recommendation for AR. Same thing with kurtosis. So, you know, all four of these tests we want to consider. You know, holistically speaking, we want to take them in mind if we have issues with them. But Peter, our statistician, had kind of put together the design behind this. And so he put these in order, 1, 2, 3, 4, with a purpose in mind, not just arbitrarily, but really as the level of concern, perhaps, that you should have if there is some deviations and issues here. So it's a little beyond my scope and understanding, but from what I understand, Levine's definitely, if there's any issues, 100%, you really should take an action. Shapiro-Wilks is one step behind that. Yeah, it's pretty important. You can start to haggle and consider if like the skewness and kurtosis are maybe close on the fence, and you don't really want to, you know, apply, you know, an action code. There could be a rationale for not. Probably simplest is to ask your statistician, you know, at that point for a little guidance. You know, it might be a little bit sensitive to the type of research you're doing and maybe even the philosophies of the statistics you're doing. There's one thing I've learned from statisticians is you just get two of them in a room and it takes only 3 minutes to find something that they don't exactly agree on. So, so one of those cases where, you know, might be good to at least be consistent in how you do it, but for sure, it's kind of a descending order of really important. And so in our case here with the Shapiro-Wilks having an issue, we do really want to consider taking an action and not just brushing it off. Real quick, there was a question that came in. If the data comes up with IID on just the assessment values, would you leave it as is or use the default action code for that assessment type? So are we kind of considering the basis here? So I guess most typically, the IID would tell us that the test didn't fail. And so if the test didn't fail, then no matter what you pick here in the basis, it'll still have IID. Essentially, this basis is more or less a filtering of which actions we should take if there is an issue, if that makes sense. So IID, it really doesn't matter what you pick for basis then. That's a real good question, but if we do have a proposed action, then we, in theory, could hypothetically have it filtered down based on this basis. And you can kind of see when I choose that, this table up here, some of those columns disappear because since this is a percentage, we really wouldn't consider the square root. That's going to make a mess. That's not going to help us. So it really is just kind of tossing out some of the possibilities and focusing in on the ones that would be the best. Great question. All right, so for this assessment 12 here, we see that we have Shapiro-Wilks is a problem, and we have AR. So this one's just a little different. It's not one of our 3 data transformations that we had talked about before. And you can see that in the comment here, those transformations, those 3 that we've talked about, they do not improve the normality. So if I actually, let me switch back to assessment values just to illustrate that up here at the top, you can see the results. If we were to apply an AL or an AS or an AA, those 3 data transformations that we could do, just looking across the p-values for the Shapiro-Wilks, not one of them is not significant at all. They are all very significant. So no matter what we do for a data transformation, it's that we're not going to get that normal distribution that we need. And just scanning the data, we can see why there's tons of zeros, but then here in the untreated check, in particular, we've got 20s and some 5s and 4s and some assessments. So it's really not even remotely close to a bell shape. And so none of those 3 options help us. And so we have AR, which is our non-parametric statistics. So we choose that action code there. Now we will actually, just in this specific column 12, instead of running the AOV that we do for all of these other assessments in the report, which we'll generate in just a minute to see this, it'll actually be a non-parametric, really the ranking, a rank-based test for just this one column. Kind of one of the nice things that does actually fit in pretty nicely to our existing reporting structure. So it really doesn't stand out as anything different in the report, other than we'll see some footnotes to make sure that the difference is noted, but it fits in nicely. There's not some separate report we have to go to do non-parametric statistics or anything like that. Now we did mention spatial models. I'm not going to spend a lot of time on that, but there is a box here at the top where you can include spatial models, essentially in the toolbox of things that diagnostics can consider for you. And you'll see now in our list, we have a bunch more columns, a bunch more potential things we could do. And there's actually a couple more codes down here that are related to that spatial statistics that we're doing. The number one thing to consider with the spatial model is your trial map needs to be accurate. Otherwise, it will just be junk that is giving you. Number one, where your treatments are and which plots, and then also in your settings, the layout settings, that you have your alleyways marked as well to really be accurate. So that would be the very first thing to consider. If there's any chance that map really isn't accurate, don't even consider the spatial model, because all those calculations will be wrong. And as we alluded to in the slides, typically it's kind of a last ditch effort if things are not working statistically. Really looking at your blocking. So maybe there was we expected the gradient in a certain direction, so we did the randomized complete block, and then it turns out it was totally a mess, and our blocking didn't help us at all. There's tools here for the spatial models, but some of it's over my head, the math and the statistics behind it, and some of it's kind of outside the bounds of just a simple data review. But that's how you can kind of incorporate that into this decision making here. But I usually like to leave it off to keep things simple. And statistically, I think too, it isn't something you would just turn on all the time, but really more of when you're in the weeds and really looking at something that isn't making sense or not really lining up. So we chose AR in this assessment. Really, I think the last thing we've got here on the dialogue is this button here, Save to RStudio, or R or SAS. So all of this analysis here we're doing on this diagnostics is actually utilizing the statistical program R. It's running behind the scenes, and ARM is just performing a script and presenting the information. So if you utilize R, you can actually essentially download the script that ARM used to give us all of these values. Whether you're using the RStudio or R itself, either one of those, it'll give you the script that's equivalent to what we have here. So then you can manipulate it, or look into it further, or whatever you'd want to do with it. And then we have the equivalent of that code in SAS as well. So you could open it up and see what we're doing. You could take it and go even further with it. Totally up to you on that. But that's what that button is for. And last but not least, there is a third section to this panel, but we just see it very, very rarely. There is an outliers check that's being performed. And if there was an outlier identified in that calculation, there would be a third little section of this panel pop up and show you what plots those are. The calculation for that outlier is pretty conservative in the fact that it will not give you very many outliers. So it really is meant to be, oh wow, there's an outlier. That's crazy. I never see that. To really find values that really don't make sense. And so if you're curious, it uses this max standard residual. I think it's residual. Yep, max standard residual value here. And if there's one that's, I think the cutoff's 3.4. So if you were to have something higher than 3.4, that's what would trigger the outlier. Like I said, I try to rig it up, just making up data to try to rig it to show that, and I can't. you can't just systematically even make one. It's kind of funny how that works, but it does its job in that fact that it's not going to give you kind of a false positive of an outlier. Whereas some of our outlier calculations, like the box whisker, gives you more of them from time to time. And then you have to decide, is this one or not? But it'd be pretty much a slam dunk on if you see it on the diagnostics that it's an outlier. So that's really the diagnostics panel. That's really all the tools here we have to go through everything. To follow up with the non-parametric statistics, I think I just want to go to our print reports. We won't spend a ton of time here, but I just want to generate an AOV means table. And I'm just going to choose student Newman QLs and make sure I've got the brief table. Actually, I don't think I want to preview it here. That's going to be too small for us. So let me go next, and we'll be able to use my full screen to see. Mostly just to show. I'll zoom in a little bit. Each assessment column we have, we can see that action code visible here. So in columns 1 and 3, we really didn't have any actual changes. In column 2, we have a DAS to kind of try to highlight that these values here are de-transformed, the weighted means. But the big thing is we took the raw data that was entered, and then behind the scenes, we performed a square root calculation and then did the analysis on those values. And so that way we can trust our AOV because we're fitting those assumptions. And we do that here for each of those assessments that needed that correction. And just to highlight column 12, we had that non-parametric, but just at a first glance, it's pretty normal and nothing looks too out of place. But what we actually did, I think if we go down here, we'll see a little bit of a difference when we're looking at these statistics. There's a footnote here marked R, which is that mean comparisons are based on the plot ranks. So we did the rank analysis instead of the typical AOV, and therefore we kind of blank out the standard deviation, the grand mean, the CV, because none of those make any sense in the non-parametric realm. If we're just dealing with ranks, that's not even used. So I would kind of draw that out here to make it clear that something was done differently. But overall, we can still make the same type of comparisons. We get the comparison of the rank means instead. So that's the column diagnostics tool for data review. I alluded to it a little bit earlier, that there are some other tools that have been used historically before. There is this column properties. So instead of column diagnostics, there's a column properties. Kind of similar, we kind of structured the newer diagnostics panel based on what we had here in the column properties. There is an outliers calculation, a little bit different than the one that's newer on the diagnostics. But there is, oops, I forgot to pin that properties down. On this properties panel, there is a much simpler recommendations engine here. And this really is quite a bit different, actually. In this case, there's just a fixed button, and ARM would just tell us what, it kind of has one recommendation to give us, and here it just says it's offering to exclude treatment 1. So there's a few issues with that engine, just from a modern statistics versus statistics done 20, 30 years ago. To be frank, is really the difference. It's not that this was necessarily wrong, but just that the statistics in the industry have really evolved. And so we're kind of encouraging people to move away from that system. It's not just found on the column properties. This very same engine of what to do is also in the print reports. And so it's kind of a conversion that we're trying to encourage people to do. This was really slick that in the reporting, and you would find it in the general summary. Down at the bottom, there's an option to apply automatic transformations or treatment exclusions to data columns that violate assumptions of AOV. Really, really long option. Basically kind of describes exactly what we had done today. It's kind of slick from the perspective of what it did, that it would look at all assessment columns and basically run that recommendations tool, but the older version of it, and just present you a list. In column 2, there's this, in column 4, there's this, in column 17, there's this. Do you want to say yes to all, or do you want to do each one individually? And that was great. The key troubles with that, number one, is some of those recommendations would be to like exclude a treatment. which is really not super. That's a lot of data to throw away just to fit the assumption of AOV. So that didn't always work well. And maybe, at least in the statistical realm, the bigger difference is that it was testing on the raw data. So if we looked at that column diagnostics, that was basically the difference between looking at this first column, the raw data column, versus using the residuals to make our decisions. And I'm not an expert on the difference between those approaches, other than I know that, like I said, 20, 30 years ago, that's what was done. And there's textbooks that we use to build that old engine, both in the column properties and in the reporting. That was the way it's done. And now here we find ourselves many years later with more tools, and really the recommendation is to use those residuals to base our decision on. And so that's what the diagnostics presents. So long story short, the moral of that is I would recommend the more modern statistical approach to come into your report options. If you are seeing those questions when you generate your report, just set this option to no, kind of turn off that old way, and then move to the column diagnostics panel instead as a tool for the more modern statistical approach. All right, well, we've reached our hour. I think I've exhausted my mathematical and statistical portion of my brain quite enough. But certainly, if you have questions, I have another minute or two if you had them. But otherwise, don't want to take up too much of your day. So I appreciate everyone joining today. So hopefully maybe we'll see you next week. Like I said, I'll hang on the line just for another minute if there are any questions, but thanks everybody for hearing us out.